Okay, so in our topic around functions and graphs, we now want to return to looking at some more graphs. But before we do that, we need to introduce the two transformations that we've omitted before now. And we haven't omitted them deliberately, we've omitted them because they haven't been necessary before now. But our next type of function we're going to look at is the exponential function. And when you get further down the track to things like the square root function, the circular functions, various other functions, we need to be able to add in, we need to be able to think about two further transformations that we haven't had to think about before now. So the four transformations that we're familiar with are listed up the top here. So we know that if we multiply the function by a number, we dilate that function by a factor of a from the x-axis. And in terms of what that does to every point on the graph, if we stretch a graph away from the x-axis, it's the y-coordinates that are being multiplied. So in that situation, every single point on the graph with coordinates of x and y would now become the point x a times y. So multiplying all their y coordinates by a will stretch the graph away from the x-axis by a factor of a. We know that when we stick a negative in front of the function or multiply the function by -1, we're going to reflect that graph in the x-axis. Okay, so what happens when we reflect a graph in the x-axis, it's not the x coordinates that are changing, it's the y coordinates that change. So every point on the graph with coordinates of x and y becomes the point x negative y. So the y coordinate becomes negative, and that sees it flip around to the other side of the x-axis. So if the y coordinate already is negative, when we multiply it by -1, it becomes positive. If the y coordinate is positive, we multiply it by -1, it becomes negative. And we see when we do that to all the points on the graph, the whole graph is reflected in the x-axis. So we've also seen what happens when we translate a graph left and right, and we've seen that this is a little bit different in terms of how it behaves in the function. It's not, we don't add or subtract outside the function, we don't multiply outside the function, we start to get inside the function. So we replace all the x's with x minus h's in the function. And the other thing we need to be mindful of here is that this sort of does the opposite of what we think it will. So when we're subtracting a number inside the function, so f of x minus 2, for example, the graph would go to the right by 2. If it's f of x plus 2, or within the function, the graph would go up by 2, to the left by 2. So translating left or right, we just need to be a little bit careful about it. It's a bit backwards from what we think. But if we think about minus h as being to the right by h units, obviously that assumes that h is a positive number, then if we were to actually do that to every point on the graph and take every single coordinate, x, y, and if we moved it to the right, it's the x coordinates that's going to be changing. And if we want to move to the right, we'd be adding h onto all the x coordinates. Now down the track, in fact not till year 12, will you see why when we add onto the x coordinates to move a graph right, in the equation does it look like a subtraction? Okay, you'll see that in year 12 when we look at the transformations in more depth. The last one is translating up or down, and that's when we add or subtract a number on outside the function. Okay, so in this case plus k, if k is a positive number, that would translate the graph up by k. So there's nothing tricky about this one. Adding on a number goes up, subtracting a number goes down. So thinking about what that actually does to every point on the graph, each point with coordinates of x and y, the x coordinates don't change if we move the graph up or down, but the y coordinates change. And if we're going up by k, we're going to add k onto all of our y coordinates. Okay. Right, so we've got a clear sense of what's happening. Well, hopefully we've got a clear sense by now of what's happening with these four transformations. What we want to think about is that there's sort of two that we haven't really thought about. So we've thought about what happens when we multiply the y values by a number. We've thought about what happens when we multiply the y values by -1. We've thought about what happens when we add or subtract a number onto the y values. We haven't thought as much about the x values. Okay, so we've thought about what happens when we add or subtract onto the x values. We go up or down. But we haven't thought about what happens if I multiply the x values by something. And if we think about that, let's say if we had, let's get a pen rather than a highlighter. Let's say if we had a parabola and we multiplied all the x coordinates by 2, for example. So this point, if we doubled its x coordinate, it would go out to here. This point, if we doubled its x coordinate, it would come out to here. We doubled this point's x coordinate, it's going to come, not that far, it's going to come out to sort of about here. Okay, and what we would see is the graph would be dilated, but we want to be able to sometimes think about the dilation as happening away from the y-axis instead of, from the y-axis instead of from the x-axis. They're both dilations, and in many cases, any dilation that we can describe as being from the x-axis, we can also describe it as a dilation from the y-axis. But it's easier to be able to make the switch depending on how it's presented in the equation. You'll just have to go with me on that for a minute. We'll come back to that in a bit when we have a look at it. We'll have a look at some graphs. The other thing we haven't thought about is what happens if we make the x coordinates negative. Now this isn't going to be as easy. I'm going to change graphs here just so I can, so let's imagine maybe a cubic graph. If I make the x coordinates negative, so if I take this point and I make its x coordinate negative, it's going to come over here. If I take this point and I make its x coordinate negative, it's going to come over here. If I take this point and I make its x coordinates negative, it's going to come over here. So if we multiply the x coordinates by something negative, we're going to see reflection in the y-axis. Now again, we haven't had to think about this before now, because in the case of the cubic, reflection in the y-axis is the same as if we had reflected in the x-axis. Okay, so it doesn't produce a different graph. Whereas we're going to introduce a graph shape in the next video where reflecting in the y-axis will produce something very different to reflecting in the x-axis. Now the other reason I changed from the parabola was that if you have a parabola and you reflect that in the x-axis, because it's already, sorry, in the y-axis, because it's already symmetric about the y-axis, you don't get a new graph, you get exactly the same thing. So we haven't had need to think about reflection in the y-axis before now. So the two things we want to think about are the graph of y equals f of x after dilation from the y-axis. Now I'm going to leave the factor for a minute because we need to, we're going to explore what this looks like by a factor of, and I'm going to come back and fill that in a minute. And we also want to think about the graph of y equals f of x after reflection in the y-axis. Okay. All right, so you might be able to think about, you know, what that's going to look like just looking at the equations. So the only thing that we've looked at so far where we affect the x coordinate is this one. And that's the only one where we've been doing things inside the function. Everything else has happened outside the function. So when we multiply the y coordinates by a value, that's the same as doing that same value times the whole function. When we multiply the y coordinates by -1, it's the same value of doing the whole function by -1. Okay. When we add k onto the y coordinates, it's the same as adding k onto the function. Okay. So the only one we've looked at, haven't looked at is, the only one we've looked at where we're actually dealing with adding or subtracting or multiplying inside the function is the translation left or right. So you might be able to make a prediction here about what you think it's going to look like in the function to dilate by a factor, to dilate from the y-axis, and what it might look like in the function to reflect in the y-axis. Let's just have a play around with some graphs. I'm just going to pause this video and change over to a graphing program, and then we'll come back here and fill things in. Okay, so this is a graph that you're not familiar with. This is actually the square root graph. Y equals the square root of x. We used to teach this in Year 10, but it's actually not in the textbook anymore, so we won't be covering it, but you will meet it reasonably early on in Year 11. The reason I introduced this graph is because you can see that we're not going to get this. If we reflect this graph in the y-axis, it'll produce a different shape from what we're seeing there. If we reflect this graph in the x-axis, that's a different shape again. So we get three different things depending on whether we haven't reflected, we've reflected in the x-axis, or whether we've reflected in the y-axis. And so I want to use this shape to illustrate what's going to happen. So at the moment, I've just looked at the two different dilations. So the A out the front, that's the dilation we're familiar with. Dilation from the x-axis, and we know if we make that A value negative, it'll reflect in the x-axis. So let's have a play here. If we make A bigger, so we can see if we focus, for example, on what happens to the point 1, 1. So the original graph goes through the point 1, 1. That's probably a good point to think about. Drawing in this is hard, but if we think about what happens to that point when we do the dilation. You can also focus on it also goes through the point 4, 2. So you might want to keep an eye on those 2 points and what happens. So as we dilate A away from the x-axis, we think about what we're doing is we're multiplying the y coordinate by, at the moment, let me make it a whole number. So in A is 2, we've stretched away from the x-axis by a factor of 2, we've multiplied the y coordinate by 2, and we're now up here. We've multiplied this y coordinate by 2, and we're now up here. Okay. So what we want to think about is, and we also know when we make A, so obviously if we made A smaller, if we made A half, we'd have halved the y coordinate, so we're seeing that as well. And if we, I'm just going to delete those notations quickly. Okay, so if we still with A. If we make A, so putting A back to being 1, there's the original graph, goes through that point 1, 1 and that point 4, 2. If we make A half, we halve all the y coordinates, it now goes through 1, 1 half and 4, 1. If we make A negative, we know that the graph reflects under the x-axis, and we also have dilation happening. Okay, so again, let's go back to this original function. So I'm going to make A1. And now let's have a look at B. So what you can see is B, we're not multiplying the square root of x by B. We're multiplying x by B. So this is an inside the function thing. Here we've got the square root of B times x, as opposed to A times the square root of x. Okay, so again, it's about multiplying just the x part of the function within the function rather than multiplying the whole function. So if we have a look at what happens here, as I make B bigger, keep an eye on what's happening. So we know the original graph goes through 1, 1 and 4, 2. As I make B bigger, okay, it does look like it's also dilating from the x-axis, and in many ways it is. Let me make this a whole number. Okay, so here B is 2. So it's clear it hasn't been dilated from the x-axis by a factor of 2. Okay, this stretch in this direction is not by a factor of 2. Okay, but interestingly, this stretch in this direction is not by a factor of 2, but it is by a factor of a half. That's the point half 1. This has now gone to 2, 2. So the y coordinate was halved when we made B 2. If we make B 3, it's going to be hard to tell, but actually what has happened there is that we've now got a third of the y coordinate. We've now got a third of the y coordinate. Let's make B 4, because we should be able to see then that if we take a quarter of 4, it should come back here to 1. So if we make B 4, we indeed see that that point that was at 4, 2 is now in at 1, 2. So the the x coordinates have all been multiplied by, not by 4, but by a quarter. Okay, so as we make B bigger, the graph squashes towards the y-axis. So the reverse should therefore happen. Let's put B back to 1. And see, if we were to make B a fraction, so if we were to make B smaller, we indeed see that the graph is stretching away from the y-axis. Okay, so let's go back to there where B is a half. Okay, so where B is a half, let me just see if I can get rid of these notations. Okay, so I've just erased those notations. I've still got those 2 points that were on the original graph circled, so 1, 1 and 4, 2. And now we've made B1 half, and we saw that the graph stretched away from the y-axis, and we can see that the x-coordinates, in fact, have doubled. We're actually off the chart there, but it will have doubled up to 8. Okay, so the y-coordinate double when the b value is a half. So it's not just a dilation from the y-axis by a factor of b. It's actually a dilation from the y-axis by a factor of 1 over b, the reciprocal of b. Okay, so that's the first thing. Now you remember when we know that when we translate left and right, everything's a bit backwards from what we expect it to be, and the same is true when we do anything that happens sort of inside the function. Now sorry, let me just go back. Let's just go back to b is 1. Okay, so again we know that b is 1. Let me just circle those 2 points again. We know we go through the point 1, 1 and 4, 2. Okay, so if I were to make b smaller, as we know, it dilates from the y-axis, but the minute b becomes negative, let me move this out of your way, we can see that. So at the moment b is, let me make b negative 1, we have reflected in the y-axis. Okay, so when we multiply just the x part of the function, not the whole function, but just the x part of the function by negative 1, so f of negative 1 times x, or f of negative x, we reflect the graph in the y-axis. Okay, and you can see in this instance how that produces a very different shape to what we get when we reflect in the x-axis, and so therefore it's important to be able to talk about this transformation. Okay, I'm going to go back over to the notes and we'll work through some examples, and we'll just complete that table at the top. Okay, so we already speculated that we were going to think about dilating from the y-axis and reflecting in the y-axis. Now, when we dilate from the y-axis, the function is f of bx. Okay, so we multiply by b inside the function. So it's like this one. Okay, we don't multiply the whole function by b, we multiply x by b, not f of x by b. And the other thing we noticed is that it's not by a factor of b, that's by a dilation factor of 1 over b. It's the reciprocal of b. So remember, reciprocal is when we flip a fraction. So if we had m over n, the reciprocal of that would be n over m. So therefore, when we have just a whole number, b, the whole number is b over 1. When we take the reciprocal of that, we get 1 over b. And similarly, if we have a fraction, so if we're going to have f of half x, that would be a dilation by the reciprocal of a half, which is 2 over 1, which is 2. Okay, dilation by 2 from the y-axis. So f of bx is going to dilate by from the y-axis by a factor of 1 over b. And when we reflect in the x-axis, it's also about it all being inside the function. It is when we get f of negative x. It's going to reflect in the y-axis. Okay. So when we do things inside the function, like what we're doing here, they affect the x-coordinates of the function, and therefore it's about dilating from the y-axis, reflecting in the y-axis, translating left and right. When we do things outside of the function, okay, it is going to affect the y-coordinates. It's about dilating away from the x-axis, reflecting in the x-axis, and translating up or down. Right, so we've now got our full set of transformations, and that will be a big advantage going into the next couple of years as you start to meet some additional graphs. Right, one of the things I want to have a look at is, I did touch on it when we were over in the graphing screen, why we haven't really had to think about this before now, and I'm going to think about that in the context of these two graphs that we're familiar with, the parabola y equals x squared and the cubic y equals x cubed. So the graph of y equals f of x is pictured in each of the following. In each case, sketch the graph of y equals f of negative x. Okay, so f of negative x means we are going to reflect in the y-axis. Okay, so any point, we can pick a point. The point, 2, 4, we reflected in the y-axis, it goes to the point negative 2, 4. The point 1, 1, we reflected in the y-axis, it goes to the point, the point negative 1, 1, reflecting the y-axis, it goes to the point positive 1, 1. And we can see here, because this graph is symmetric about the y-axis, if we reflect it in the y-axis, nothing new happens. Okay, so in the case of the parabola, let's try and actually get it on top of that red graph, y equals f of x is the same as y equals f of negative x. Let's be clear about why that's happening. So if we're saying that f of x here is the basic parabola y equals x squared, then f of negative x is negative x all squared. So again, replacing all your x's with negative x's. Okay, so we know that negative x all squared is just x squared, and so therefore this is the same as f of x. That's why graphically it doesn't look any different, algebraically it doesn't do anything any different, which is why we haven't had to think about reflecting in the y-axis when we've just been dealing with quadratics. The second graph here is a cubic. When we reflect that in the y-axis, this point at 1, 1 is going to come over here to negative 1, 1. This point at 2, 8 is going to come over here to negative 2, 8. This point at negative 1 is going to be at positive 1, negative 1. Negative 2, negative 8 is going to be at positive 2, negative 8. 0, 0, reflecting that in the y-axis doesn't go anywhere. And so we're going to get this shape here. So this is y equals f of negative x. Now again, we haven't actually thought about this with the cubic before now, because actually if we reflect in the x-axis, we also get this same shape. Okay, so we also know that this is actually the same as if we had done negative f of x. Okay, so that's why we haven't had to think about it before now. Let's have a think about that. So if our original function was x cubed, we know that negative f of x is negative x cubed. That's a reflection in the x-axis. Okay. We know that f of negative x means replacing the x's in the original function with negative x's. So we get negative x all cubed. And if we do negative x all cubed, negative x times negative x times negative x, it is negative x cubed. And so it's the same as the reflection in the x-axis. So this is the reflection in the y-axis, and what we're seeing here is that these are the same. Okay, and so again, that's why we haven't had to think separately about reflecting in the y-axis when we've just been dealing with quadratics and cubics. Okay, but you saw in the square root graph how we get something different happening, and so we need to be able to start to talk about this as a separate thing. Okay, let's have a look at example 2 here. The graph of f of x equals x squared is pictured in each of the following. Sketch the graph of y equals f of 2x on the axis provided. Okay, f of 2x, this is what we've just been looking at. So this is a dilation from the y-axis, dilation from the y-axis, because it's inside the function, not outside the function, but it's not by a factor of 2, it's by a factor of the reciprocal of 2, 1 over 2. So if we dilate from the y-axis by a factor of a half, that means we need to halve all the x-coordinates. That's going to dilate from the y-axis by a factor of a half. So the point that is at 1, 1 is going to come into half 1. Okay. The point that is at 2, 4 is going to come into 1, 4. The point that was at 3, 9 is going to come into 1 1/2, 9. The point that's at 4, 16 is going to come into 2, 16. So we are dilating by a factor of a half from the y-axis, and we can do the symmetric points over here. Same ideas. Obviously we can, sorry, that's not halved. So we are dilating in by a factor of a half. And we get this, that is y equals f of 2x, dilated by half from the y-axis. We also want to sketch the graph of y equals 4 times f of x. Okay, so this is multiplying the whole function by 4. This is dilating by a factor of 4 from the x-axis. Alright, so the point that was at 1, 1 comes up to 1, 4. The point that was at 2, 4 goes up to 2, 16. Okay, and obviously symmetry, negative 2, 16. Okay. Okay, now what we actually see here is that we've ended up with the same graph. And so that's why we didn't need to think separately about dilation from the y-axis with the cubic, because, sorry, with the quadratic and also with the cubic, but that's going to be different, because we can think about it, we can instead expand it out and worry about it as a dilation from the x-axis. So if you think about the dilation from the y-axis by 2, dilation by, sorry, not 2, by half from the y-axis, that means that we get f of 2x. Now, if our original function is f of x equals x squared, that is 2x all squared. But if we expand that out, that is 4 times x squared, which is the same as 4 times f of x. And so these are going to be the same. Okay. So this 4 times f of x is a dilation by 4 from the x-axis. And so what we're seeing is, in the case of the quadratic, those two dilations are the same thing. Now I want to be really clear about the fact that this wouldn't be true for all other functions. So if our original function, let's say, was a cubic instead, f of x equals x cubed, and we dilated it by half from the y-axis, so it would be 2x all cubed. If I expanded that out, that doesn't give me 4 times x cubed, that gives me 8 times x cubed. And so what we see in the case of the cubic is that dilating by half from y is the same as dilating by 8 from x. So I want you to there are no blanket rules. Okay, there is no way you can say that for all functions, when I stretch by this factor in this direction, it's the same as stretching by this factor in this direction. So there's no real rule, so you still need to be able to think about them separately. But the point I make is we didn't need to worry about this dilation with quadratics and cubics, because we could instead write them as dilations from the x-axis rather than dilations from the y-axis. That's going to change when we look at our exponential functions in the next section. Okay, so we can combine all these transformations together. We're familiar already with these things, okay? Dilation and reflection from the x-axis is the A. Translation up and down is the k. Translation left and right is the h. And now we've also got another thing inside the function, which is dilation from the y-axis by 1 over b, or reflection in the y-axis if b is a negative number. Okay, so let's sketch some graphs here based on transformation. So here we've got pictured the graph of y equals g of x. And we want to draw the graph of y equals g of negative x minus 1. Okay, so the negative x is going to mean we reflect in the y-axis. We always do dilations and reflections before we do translations. The negative 1 here means we're going to translate down by 1. Oops. So we want to take each of the points on this graph, reflect it in the, sorry, I wrote x-axis, reflect in the y-axis. X-axis would be the negative out the front. We're reflecting in the y-axis and then translating down by 1. So we want to do that with each of the points. So let's think about this point at negative 1, 0. If I reflect that in the y-axis, it's going to come over here to positive 1, 0. And if I then translate it down by 1, it's going to be down here. I'm just going to mark myself a scale so I can be clear. So if that's 3, okay, so maybe it's not quite that far. If that's 1, 1, that's 2. Okay, just trying to get a bit of a sense of the scale. They're a bit big. Okay, so reflecting the y-axis, as we said, it's going to move it over to positive 1, 0, and then down by 1. It's going to be here at positive 1, negative 1. Okay. If we take the point 0, 3 and we reflect it in the y-axis, it's not going to go anywhere. Reflecting in the y-axis is about multiplying the x coordinate by negative 1, so it won't move anywhere. But then down by 1, it's going to move down. So it'll be at 0, 2. Okay. The point 2, 3, reflected in the y-axis, it's going to come over here to negative 2, 3. Down by 1, it's going to come down to negative 2, 2. Okay. You might take some other points. I'm just going to move that coordinate so it's not so crowded so we can see what's happening. You might just think about this point. I don't know the exact coordinates of this point, but if I reflect in the y-axis, it's about here, down by 1, about here. Okay. Reflect in the y-axis down by 1. You might just think about some points. So we're going to have our graph come down here, turn here, and down here. Probably got that bit out a bit. Should be a bit steeper, I think. Okay, so reflected in the y-axis and down by 1. So marking the new coordinates of all of the points that you transformed. So we had 3 original points that we were given, so mark those new coordinates. We've got enough information to work that out. Okay, let's have a think about another one. So example 2, we've got the graph of y equals f of x is pictured. Sketch the graph of 2 times f of 2x. Okay, so this 2 is a dilation by 2 from the x-axis. Actually, I won't write that there because it's going to get in the way of the graph, I think. So we're going to have that 2 and that 2. So that's a dilation by 2 from the x-axis. The 2 inside the function is a dilation by not 2, 1 over 2, the reciprocal of 2, from the y-axis. Okay, so we're going to be dilating in this way by a half and up this way by 2. Okay, so we're going to be halving all the x coordinates and doubling all the y coordinates. So this point at 1, 3, we halve its x coordinate, it's going to be half. We double its y coordinate, it's going to come up here to, half 6. Okay. This point here, we halve its x coordinate, won't go anywhere, so the dilation from the y-axis doesn't change that, but dilating by 2 from the x-axis, we double its y coordinate. It's going to come down here to 0, negative 2. This point here, halving from the y-axis, so half of 2 is 1, and then dilating by 2 from the x-axis, so stretching away from the x-axis, doubling its y coordinate, it's going to come down here to 1, negative 2. Okay. And so we've got this graph that now is going to be taller and thinner because it's both squashed in towards the y-axis and also stretched away from the y-axis. The graph of y equals g of x is pictured. Sketch the graph of negative g of 3x plus 2. Okay, so we've got 3 things to think through here. Okay, so we've got the negative out the front, which is going to be, that's the first thing we need to do. I was just trying not to get my arrows crossed, but they're going to cross. So this is reflection in the x-axis. Okay, the 3 here is going to be dilation by 1/3 from the y-axis, okay, and the plus 2 is going to be translation up by 2. Okay, so we want to take each point, we want to reflect it in the x-axis, which will make its y-coordinate negative. We want to then dilate it by 1/3 from the y-axis, which will multiply its x-coordinate by 1/3, and we want to then translate it up by 2, so we'll add 2 onto its y-coordinate. So let's do that to each point. Let's start with the point 0, 0. If we reflect it in the x-axis, it's not going to go anywhere. If we dilate it by 1/3 from the y-axis, it also doesn't go anywhere, and then we want to move it up by 2, so it's going to come up here. Just going to get some scale happening again. Okay, so we're going to come up here, it'll be at 0, 2. Let's take the point 1, 1. We reflect it in the x-axis, it comes down to 1, negative 1. We then dilate it by 1/3 from the y-axis, it's going to come in here to 1/3, negative 1. And then translate it up by 2, it's going to come back up here. So it will be at 1/3, positive 1. Take this point, reflect it in the x-axis, it's down here. Dilate it by 1/3 from the y-axis, it's in here. So we reflect it, we dilate it, and then translate it up by 2 again, and it's going to be up there. Okay. So this is now the point negative 1/3, 1. And if we join up those points with the same graph shape we can see originally, we get this new graph. Y equals negative g of 3x plus 2. Okay. So I want you to be able to think through those transformations just like we did back at the start of this topic, but we're adding in the 2 new transformations and be able to use those transformations to sketch new graphs. So again, there's a worksheet to work on for today.